After illustrating the Dirac's measure on a separate video, let us try to really show that a Dirac's measure is a measure. Hence, we need to show that the definition of the Dirac's measure, I'm going to immediately proceed to the piecewise function. The mu of any e, which is e, is a subset of x or an element of the power set of x, is defined as 1 if a certain x sub o is an element of e, or 0 if a certain x sub o is not an element of e. Again, we're able to illustrate this in the previous video. The point here is to really show that this is actually a measure. And take note that the definition of the measure is in this manner. Okay? A function, I will be writing here the definition so that we will be guided. Mu, map of our script m to the interval 0 and positive infinity, is where our script m is a sigma algebra, is a measure if it satisfies the following. Okay, the first one that need to be satisfied is that the mu of the empty set, okay, is equal to 0. So we are going to check whether the empty set, mu of empty set for this definition of Dirac's measure is really equal to 0. If it's satisfied, we'll be proceeding to the next condition. But if it's not, automatically we can say that Dirac's is not really a measure. Okay, and here the second condition is if we have the set of a sub I where I is an integer is a disjoint collection of sets in M, or your script M, then it should satisfy this form. We have here the mu of your union of a sub I for I starts from 1 to infinity, okay, meaning the union of the disjoint collection of sets must be equal to the summation of the mu of your a sub i's, where I starts from 1 to infinity. So they will be showing this later as well. Now, let's try to start. I'll be separating this portion so that you will not be confused with what to do. Okay, so our proof here works like this. Okay. Now, for the first situation, okay, we need to show that for the mu of empty set is equal to really 0. So we have here, since empty set does not have any element, right? It doesn't have any element, right? Okay, does not have any element. Okay, then x sub o should not be an element of the empty set. Okay, hence the mu of your empty set, since it doesn't have any element and x sub o should not be an element of that, that would mean the answer here is this portion, the second statement. Since x sub o is not an element of that set E, in this case empty set, here we're able to satisfy the first condition. Now let's proceed to the second condition now. Okay, the condition should be for this type of set, which is a collection of disjoint sets, we will be able to show this. So from here, let us also try to introduce the set. Let a sub I for all I element of natural numbers is a disjoint, that's disjoint collection of sets in your script M. Okay, so we need to introduce that. However, take note, there are two statements here that we need to satisfy. In short, we will have two cases. The first case is case 1, if x sub o, that's case 1, if x sub o is an element of the union of a sub I, this portion here, I from 1 to infinity. And the second later on is if it's not. So whatever be the result of this, we need to show that it's also equal to the result of this here, using some logical and relationships. Okay. So for case 1, then x sub o should be an element of a sub I. We don't know what that a sub I here, because if we talk about a sub I being, the set of a sub I is a collection of disjoint sets, that would mean x sub o should be an element of one. Okay, one of them. Because, of course, x sub o should not be an element of more than one, because, again, it's a disjoint. But since it's an element of the union, so there must be one a sub I, okay, for some I element of natural number, where x sub o is contained into that. Again, only one a sub I, because, again, a sub this set is a disjoint collection. Okay, so at least we're able to establish that x sub o is already there. So, hence, we can say that x sub o is not an element of another, let's say, a sub j, for j is not equal to I. Okay, so if x sub o is an element of a sub I, it should not be an element of a sub j. Again, because they are disjoint collection, x sub o should only be contained in one. Okay, what does this imply? What does this imply now? This the point here. Okay, again, we can say here, since they are disjoint. Why do we need to establish this? Because if we are going now to take the summation, okay, so let's say, for example, the mu of a sub I, since x sub o is included there, so we'll be using this 1, right? It should be 1. And the mu of a sub j, okay, since x sub o should be 0, such that when we add them, the summation, this will not also reach more than 1. It will only be equal to something that is equal to this. So the point of that will be clarified further as we move to the next portion here. And here is what I am going to point out here. The mu of the union of a sub k, for k is equal to 1 to infinity, can be broken down into the mu of a sub I and the summation of other a sub j, where j is not equal to I, right? So for all the rest where a sub I is excluded, because x sub 0 is here, so x sub o should not be in any of this, because, again, they are pairwise disjoint. And what does this imply now? Take note that from here, we're able to forget that here. That would mean that the mu of the union of a sub I starts from 1 to infinity, and since x sub o is included there, so automatically this is the first statement. This is equal to 1. We need to show that this, which is equal to, let me separate or rewrite this for the meantime, okay? Because this is the summation, the summation of the union, mu rather, of a sub I, where I starts from 1 to infinity. We can break them into, again, taking out a sub I and those which are not a sub I. Take note that x sub 0 is in a sub I, so this would be 1. The mu of that is 1. And since x sub o is not in any of this, because, again, they are pairwise disjoint, whatever be the sum of this, let's say 0 plus 0 plus 0 plus 0, because x sub o is not an element, we'll be using the second statement. This is still equal to 1. So the summation of the mu of a sub I, where I starts from 1 to infinity, is 1 plus all these zeros, so it's just equal to 1. And this is just equal to here, this expression, the mu of the union of a sub I, where I starts from 1 to infinity. Hence, we're able to establish this connection for our case 1. Okay? For our case 1, when x sub 0 is an element of the union. So that's already okay for the case 1. How about for the case 2? Let me use another space or another page here. Okay. Let's have here case 2. If x sub o is not an element of the union of a sub I from 1 to infinity. Okay? So that would mean, then, just for this alone, because it's not an element, we will be using 0 here. Hence, then, the mu of the union of a sub I from 1 to infinity is equal to 0. That's already obvious because it's not an element, right? Now, what we need to show here that the mu of the union, that's the union of a sub I. We can remove those parentheses. A sub I from I to 1 to infinity must be equal to the summation of the union of the mu rather. Sorry for that. A sub I where I starts from 1 to infinity. This is again the target here. So we're able to take about case 1 earlier. This is now case 2. So how can we show this now? Okay. So since this is not let's use some logic here. Since x sub O is not an element of any of the union of the pairwise disjoints. Okay. If it's not an element in any of those a sub I, the union of all this a sub I, and since we're talking about union, so x sub O, this means that x sub O should also not be an element of a sub I for all I element of n. Because if x sub O is an element of just one, it will appear here because this is a union of all. So since we consider that x sub O is not an element of the union of the pairwise disjoint, so it could not be an element of any. Okay? It could not be an element of any. Therefore, then the summation of all the mu of a sub I from 1 to infinity, since x sub O is not an element of any x sub I, so it's not an element of a sub 1, nor a sub 2, nor a sub 3, nor a sub 4, nor a sub 5, so on and so forth, right? This would mean it's 0. Because it's not an element of all. Because here, it's not an element of E. It's not an element of a sub 1, not an element of a sub 2. Again, because, it's not an element of union, then it should not be an element of any of those sets. So with that here, this and that, okay, we were able to establish that the mu of the union of a sub I, where I starts from 1 to infinity, when x sub O is not an element of that, is just equal to the summation of the mu of a sub I, where I starts from 1 to infinity. So we established this for case sub 2, where our x sub O is not an element of the union, and even in case sub 1, where x is an element of the union. Okay, we're able to establish that here. So in short, case 2, let's have here, is satisfied. The second condition for our measure function. With earlier, our first condition already satisfied, and the second condition now be satisfied, then, therefore, the mu for the Dirac's measure is a measure function. Now this is even shorter than proving counting measure, because in counting measure the idea there is infinity and finite of the sets. Here we're just talking about whether x sub O is in the set or it's not in the set, so it's even shorter, but nevertheless this is how we prove the Dirac's measure to be really a measure using the definition of a measure function. Thank you very much for watching.